Hello and welcome to episode 2 of my data structures and algorithms series. If you've missed any of the previous episodes and you want to get caught up, check out the playlist linked right up here, and be sure to get subscribed to me so you don't miss any of my future videos. In this video, we're going to be covering the most basic data structure, the array, and then as an extension of that, we're also going to be covering lists, which you will see coming up all the time in data structures and algorithms. I'm sure that most people are already familiar with arrays if you have any experience coding, but we're going to go over the actual data structure side of it just to give you a quick refresher and something to build on. So an array is essentially a fixed sized, ordered collection of items that are stored at contiguous memory locations. The main things to know about when we talk about arrays is that they will have things of only one data type, which is essential for how their model works because everything has to take up the same amount of space. For example, they could have ints, floats, strings, whatever else. And since they're stored at contiguous memory locations, you can very quickly access random indices because you can just multiply whatever the size of the data type in the array is, and then go ahead and find the correct memory location to find whatever index you want. And also they have a fixed size, which means that they can't grow past whatever you allocate them at the start. So since we're going to be dealing with like high level languages here, and by high level I even mean like C, I don't just mean like Python and stuff like that, I mean anything above like assembly really, we can extract away any of that memory related aspects and distill an array down to its most important sort of concepts that are related to it. The first important thing is the array's data type, which just talks about what type of data is stored in the array. The second important property is going to be the array's size in memory. So this is often referred to as its length, which is what the property is called in languages like Java. This is a separate property from the array's size, which is how many items are actually in the array. So this is going to not count any of the empty space that we have in the array. To wrap up this section, let's talk about the time complexity of different array operations. So things that are index-based are going to run in constant time generally. This includes item insertion into an array that has empty space already made for it, and also index-based lookup. So this makes it a great base for all sorts of data structures and a very convenient way to store data. The only issue is when you're using an array, since it is a fixed size, once you get to that size, you are out of luck for that array. You can't just keep adding in items or anything like that. And the other issue is that because an array works like this, you're going to have issues if you want to insert at the beginning or middle, for instance, and also if you want to remove items, because that is going to include having to shift over every single other item if you want the indexes to still be contiguous. Now that we've covered arrays, I just want to take a quick second to talk about strings. So strings are going to see come up a lot of the same places that you're going to see arrays come up, and that's because they're basically just immutable arrays of characters. So you can't change strings in place because I just mentioned they're immutable, but one way that you will often deal with strings and things of that sort is just to take them, convert them into an array, and then just convert them back into a string once you're done doing whatever it is that you needed to do to the string. So this is going to be very useful for any algorithm where you need to edit a string, and just know that you can pretty much treat strings the same way that you do arrays. So now that we have finished talking about arrays, we can move on to talking about lists. So what lists are still an ordered collection of items, but instead of being statically at one size, they can grow with the data as you need it and change size dynamically. So because of this, they are really great for if you need to continuously insert things in, because you don't need to allocate an array with the correct amount of memory right off of the bat. They're also good for a lot of other things depending on which type of list you're using. So we're actually going to be talking about two different kinds of lists here. We're going to be talking about array lists and linked lists. We're going to start off by talking about array lists because they are going to build directly off of the knowledge that we just gained when talking about arrays, and then we will move on to talking about linked lists, and we'll discuss what use cases are good for both of those different kinds of data structures. So an array list is a list that uses an array as the backend for how it's actually storing its data. This results in essentially the same data structure as an array, but with the added benefit that you can dynamically size it. In JavaScript, actually, if you've used arrays at all, you've actually been using array lists the entire time because every single array in JavaScript works like this. The only advantage to using an array list over an actual array is that it can dynamically size itself. There's just no other difference at all. So it accomplishes this by copying over your data to a new, bigger array every time you're going to do an insertion that's going to then exceed the size of the array that it was using before. In most array implementations, it will accomplish this by creating a new array that is twice the size of your current array and copying over all the data, but that exact multiplier of how much bigger the new array is can vary from language to language. So now let's talk about some of the runtime differences when you are adding to arrays. So if you are just going to go ahead and add an item to an array list normally, and the underlying array already has enough space, then that is just going to be an O of 1 insertion, unless you're inserting it in the beginning or middle, in which case it's going to be O of n because you have to shift over all of the other values. But if you're appending just to the end of it, then you can just go ahead and put it in there. But if you are copying, or if you are inserting past that point, then you're going to have a little bit of an issue, because first you need to go ahead and copy over all of your data to that new bigger array. So when you're doing that, it's just going to go ahead, create an array that's twice the size, and then it's going to go ahead and copy over all of that data. And then after that, let's say you wanted to put in an 85 here, then it can go ahead and put in the new value that you wanted. So this might sound like it means that insertions in an array list take O of n time, because in the worst case, you need to copy over, and copying over is going to take O of n time. But actually, the runtime for this operation is still O of 1 because of a concept called amortization. So what amortization is it's sort of a method of rolling out the runtime of that worst case operation over all of the other operations, because we know how often exactly this operation takes place, and we know what its runtime is relative to all of the other things. Let's talk about the actual math of why this is still O of 1. So when we are talking about amortization, we have our normal case of insertion, which is when we don't need to grow our array, and that takes O of 1 time. And then we have our copy case, which is going to take O of n time because we need to copy over the entire array, and we copy over at every power of 2. So then if we look at the actual math of this, we can break this down to what if we were doing n insertions, right? So our base array is going to start at a length of 1, so we just start with one spot in our array, and we will just have a variable called x, which is just going to be the highest power of 2 number that is not going to be higher than n. So what we're going to have to do is we have to double when the array has a size of 1, a size of 2, a size of 4, a size of 8, 16, on until we get to x. So we can go ahead and just flip this on its head to get something that's easier to deal with in math, and say that it doubles at the sizes of x, x divided by 2, x divided by 4, x divided by 8, and so on until we get to 1. So if we make this into a summation, we get something in this form, and if you've studied differential equations, you'll notice that this is just a very basic geometric series, and we can see that it converges to a value of 2. So because of that, or 2x in this case, because of that, we can go ahead and say that n insertions are going to take us O of 2n time because of this right here, and therefore if we divide that down, one insertion is going to be an O of 1 time, because if we divide out the n there, we get 2, and we know that we drop all of our multiples, so that's going to bring us down to 1, and therefore the insertion for an array list is going to take O of 1 time. So now we can move on to the other array list operations. So we've covered insertion, and now we can talk about removal. So in removal, you're going to have the same exact issues as you are in a normal array. If you go ahead and just remove something from the end, it'll be an O of 1 time. But in our normal case, when you're removing something from either the beginning or middle, let's say we wanted to remove this second element right here, we would need to not only remove it, but then we would need to shift this over. So because of this, removal is going to take O of n time unless you're removing from the end. So once you have all of that under control, then you can see that, and also, as we mentioned before, it's going to be the same issue for insertion at the beginning or in the middle, that you need to shift over items, and therefore it has a runtime of O of n, that we are covered with array lists, and we can move on to linked lists. So when we're talking about linked lists, we have a very separate structure. So what we have is a series of sort of small data structures called nodes, which are going to hold a value and also a pointer to the next node in the array. So, or in the list, rather. So this is an important time to talk about the two different types of linked lists. What we see here is called a singly linked list. Each node is just going to point to whatever comes before it, whatever comes after it, rather. But in a doubly linked list, we just simply add a link in the other direction as well. So from each node, you know what comes before it, and you also know what comes after it. So you'll notice that the structure is vastly different from an array or an array list, as instead of defining a contiguous block of memory that we can access, we just have a bunch of objects. So this has major implications for the runtime of different operations and makes it useful for very different things. So insertion has different runtimes for different locations, just like in an array list, but it's going to essentially be the opposite. So the easiest place to insert in a linked list is going to be at the beginning, because here what we could do if we want to insert at the beginning is we could just create our new node right here. Let's say it had a value of 5, and then we don't need to touch most of the other things in the array. Let's bring this back down to a singly linked list just to make it easier to draw. So then what we can do is just take our head from our actual linked list data structure and now point that to our new node, and then point our new node to the original first node. And now our linked list has a new item at the start. So if you want to insert anywhere else, it's still going to take O of n time, because first you have to look through the array until you get to the point where you want to insert, and then you can create your new node, and then you just need to update the pointers around it. So then the exact timing and reasoning can be applied to removing a node as well, because you need to do pretty much exactly the same thing. If you're removing from the start of the list, it's very easy. You just need to find your current head, then you need to find the next node, and then you just need to go ahead and erase the link from your linked list to your original head, and instead put it to the node that is next in the list for it. You don't even technically need to get rid of this node right here, because you still might want it to exist in data for like in memory for other reasons. So this list right here, if this is our head of our linked list, is still the exact same list as we had before, even though this node still exists. You may want to deallocate it if you're not using it, just so you don't have extra things floating in memory. So then you have the exact same thing with removing. Let's say I wanted to remove this 7. We need to look up until we get this 7, and then what we need to do is remove the link from the thing that came before it and just move it around like that so that it's now pointing to the thing that came after it. So now we finally have the issue of index-based access. So when we are doing index-based access for a linked list, you may notice that you can't just jump to the correct memory location right away. So instead what we need to do is we're going to need to traverse through the array, which is going to take us O of n time. So this also applies to any other sort of lookup, which, as you saw, is the exact reason why the other operations that we were doing also take O of n time. So when we are running through this, if we need to find the second element in the array, we're just going to start a counter, and then we're going to say, okay, this is the first element, this is the second element, and then there you go. That's how you're going to get through to it. So now we've covered the basics of both of these lists and what their runtimes are for different operations, and we can jump to talking about when the correct time to use what kind of list is. So when we are doing something that concerns accessing random elements, then we can see here an array list is definitely going to be better because you can do that access in O of 1 time instead of O of n time. But if you're more concerned with either traversing through your list linearly or making very quick edits to the list while you're traversing it, then a linked list is probably a better choice. Linked lists are also extremely useful for creating structures that are naturally recursive, because if you think about it, their definition is actually recursive, where the base state is having a next pointer of null, and then the other state where you just continue through is having a base pointer of is having a next pointer of another node. So this makes it really easy to apply algorithms to linked lists recursively, and also to traverse them recursively as well. So now finally I want to talk to you about a technique for traversing through linked lists before we end off here. So this is called the second pointer technique, and the idea is that you're going to have 2 different pointers running through this list, which will make finding certain things a lot easier. So let's say you wanted to find the middle of this list, for instance, right? There's no easy way to do that, because you don't know its length. You just know what the first element in it is. So one thing that you could do is you could traverse through it until you get to the end and then say, okay, there are this many elements. And then from there, you can go ahead and traverse through to whatever that middle element is, but that's obviously inefficient. The more efficient way to do it is going to be using 2 different things running through the list. So we'll have them both first start out at our head right here. So we'll just let's make the other one another color. And what we're going to do with these 2 pointers is just run them through the lists at different speeds. So we'll have one fast and one slow. So our slow one is just going to go element by element, and our fast one on each run through is going to go 2 elements ahead. So then if we go ahead and do that, then we will have that. And then our fast element is going to hit the end of the list when the slow element is exactly at the middle because it's going twice as fast. You can apply this to a lot of other use cases as well for having 2 pointers. So this is definitely something that you want to practice, is running through this list at different speeds so that you can accomplish different things. With that, I've covered pretty much everything I wanted to talk about when we come to arrays and strings and lists. So even if you aren't doing hard algorithms, arrays and lists obviously come up all the time, so I think it's important to have a really solid understanding of them and how they work under the hood. So these data structures form a basis for a lot of the work that we're going to be doing throughout this series, and we're going to finish up our discussion of core data structures, as I call them, which is just really the most basic data structures, and then move on to more advanced things later. So next episode, we're going to talk about trees, and then after that, we're going to go over hash tables, and then finally, we will move on to some more complex data structures as we move forward. I look forward to seeing you in the next one, and goodbye.